All right, I have the top of the hour, so we'll go ahead and get started. Good morning or good afternoon, wherever you may be. I'm Chris Spinagle from the Warning Decision Training Division. I'd like to welcome you to today's Storm of the Month presentation. Today's presentation comes to you from the National Weather Service office in Grand Rapids, Michigan. Our presenter is Ernie Ostuno, who will be presenting on radar observations of tornadic debris plumes. And with all that being said, Ernie, the floor is yours, so go ahead and take it away.
All right, thank you, and thanks everybody at the Warning Decision Training Division for setting this up and for being patient with the postponement from last month due to severe weather. So we will get going here and talk about lofting of debris by tornadoes. Is something that has been known ever since basically there's been tornadoes in the archives. There has been stories about debris being carried long distances. We had one locally here back in the 50s, our last F5 tornado in Michigan. There was a bunch of debris that originated in Hudsonville, where F5 damage was noted through western Grand Rapids, and debris was carried many miles to the northeast, and some of it was returned to their owners. We had including a fur coat that went 26 miles, and we actually have talked to the people where it started from and where it ended up, and how it got returned back to them. It's an interesting story, but there's other stories too, and the world record so far, I think, currently is 219 miles for a photograph that was lofted during one of those giant tornadoes in the big outbreak of April 27, 2011. Anyone who's done storm surveys, usually pieces of debris stuck in the ground, usually sticks or tree branches embedded in the ground that would indicate they fell from a large height. So again, debris lofting is well known, but only recently did we have the ability to actually watch it happen in real time with the radar through dual pol. So here is a video, one of my favorite tornado videos. This is a landspout type tornado picking up some plastic sheeting between the roads. I think this is a blueberry farm down in Grand Junction, Michigan. Our radar beam up in Grand Rapids is hitting that at about 3,200 feet above the ground. And I looked at the archive of this event and could not find any signs of debris in the correlation coefficient. So it's one of those deals where it probably didn't get high enough, but interesting nonetheless to see that go up in that little vortex there. So dual polarization, we could get a sense of where the debris is versus where the precipitation is, and sometimes the two will intermingle, and that will affect your correlation coefficient. So over time, we've looked at some of these cases and got a feel for what the debris plume actually looks like. And the effort here of what I've been doing the last year or two is trying to find how these debris plumes correlate to tornado strength, and that's something that we determine through storm surveys after the fact. But if we could get a good sense of the relationship between tornado strength and debris concentration and height, then in real time we may be able to get a ballpark estimate of the tornado strength of the tornado we're looking at in radar in real time. So the radar can sense the size and shape of targets, rain, hail, and snow, has known sizes and shapes, and debris is a mixture of sizes and shapes. So dual pol offers us the ability to see those scatters. You know, a lot of times they're occurring in clear air where you have like the birds and bugs and dust and that kind of thing that the radar's picking up. But in the tornado cases, obviously, we're looking at debris that's lofted, usually light debris, and that's what's going to go highest into the updrafts, such as leaves or papers, that kind of thing. And then larger pieces of debris in higher concentrations are going to give us the lower readings of correlation coefficient, and that's what we're looking for in real time to confirm a tornado via radar. So it's only been the last 10 years or so that we've put out warnings saying tornado confirmed by radar based on the debris signature. So a closer look at the correlation coefficient. You have low correlation coefficient readings, 0.8 or lower, and that's generally going to be assigned the blue color. So when we're looking at the correlation coefficient, we're looking for a little moving areas of blue that are coinciding with the tornado circulation. So we're looking at the part of the storm where the mesocyclone usually is going to be in the radar, the rotating updraft associated with the tornado. So we're looking for a blue signature in that area that's moving along with the mesocyclone and would indicate that there's a tornado underneath that storm. And then once you get into the moderate range, where you're looking at the orange and yellow colors and the higher ranges, that's either an indication that the debris is dissipating, it's becoming less concentrated, as it moves up with height. And that usually going to occur immediately after the tornado circulation ends. You'll start to see the debris, the blue, turn into lighter colors, or warmer colors, if you will, yellow and orange. And then the other situation that could happen is you get precipitation mixed into the debris. So that would give you higher correlation coefficient values. So that's how we quickly look at in real time the dual pole data correlation coefficient and try to see how the debris cloud, first identify the debris cloud and then see how it's evolving. So here's an example of that. We have a 4-panel here. There's base reflectivity, 0.5 degrees. On the upper left and then the upper right, we have storm relative velocity. And then in the lower left, we have ZDR. And ZDR, you can also get a lowering of values there where the debris signature is occurring. And then the lower right, and that's the one we are typically going to be interrogating during an event, is the correlation coefficient. And again, that purple line is the path, the damage path of a tornado that occurred here. And you can see how quick it was, only about 6-7 minutes when it did its thing. And you do see a quick firing up in the lower right there, the blue. We call these ponds or lakes sometimes because they're blue color, but you see it moving along with the mesocyclone. You also see a lot of noise there, a lot of blue dots there. So sometimes it's hard to pick out the actual debris from the background noise, which is, just your non-meteorological scatters that the radar is picking up. So basically what you're looking for is something coherent in space and time and that has vertical depth. So a lot of times we'll be, cutting cross sections in real time, which is a time-intensive thing to do, but and these things they're moving very fast and quick hitters, so you have to be very diligent on radar. A lot of times in GR2, it's quicker to do the cross sections and get a good sense of what type of debris signature you're looking at. So on the top here, we have 2 cross sections. These are both from GR2. One is unsmoothed, and that kind of shows you the noise you'll get along a radial, and then the smoothed version. And basically what you're looking for is something that's coherent in space and time again. You'll notice the blues don't get very high. That's basically because this was a quick tornado. We saw it only lasted a few minutes. Not a strong tornado, but not weak either. 90 mile an hour, EF1, low end EF1. Path length about 6 miles. The debris plume made it up to about 10,000 feet, but that was not good concentrated debris of larger pieces of building material, but more or less leaves or other type of light debris that had been lifted up that far. And it was also, you saw that storm was getting rain wrapped at the time too, so you had precipitation moving in there. So typically you're not going to see the lower values, 0.8 or lower, get as high or nearly as high as some of the lighter debris and the debris that becomes mixed in with precipitation. That part of the plume, and it's sometimes hard to find the exact top of that just because it's, contouring off the very light debris and diffuse debris. But try to get in space and time and get an estimate of the height, and that's what I did here. Here is a plan view, and this is a tornado that occurred August 20th of 2016. This was another one, EF1, low-end EF1. And you can see the typical evolution. It starts right here. You can see where the little concentrated plume is and then how it spreads out and falls back down. So you could think of this as, just looking through one slice, a plan view of the atmosphere with the debris going up in a concentrated fashion and then falling back down through the same level as it falls back down to the ground. So again, I use the analogy of a smoke plume, but there's The difference here is that it's actually moving along rather than a stationary plume from a fire. But it's also behaving kind of like a smoke plume, that it disperses as the fire is put out. It's going to dissipate and disperse. But the other thing going on here, obviously, is it's going up and then it's coming back down through the same level. So the radar is going to see it both times in plan view as it goes up and comes down. And this is the same tornado, and there's a plan view at the top left of 8,500 foot height. You can see the lighter debris or the debris that's mixing in with precipitation. So the values are lower. You don't see blues there. And then in the cross section in the upper right, you can see where the more concentrated areas of the debris was. Only got about 5,000 feet. So only about half the height of some of the lighter debris. And that's something to keep in mind when we look at some other studies, which I'll show momentarily. But you'll also see from the ground survey some really good convergence signature in a cornfield there, and some tree damage. That's a walnut tree that was shed a lot of limbs. This is a nice plan view here. You're seeing cyclic tornadogenesis. So you're seeing the same thing you just saw, except there's a cycle of 3 tornadoes. So you can see the concentrated plumes. They dissipate as the tornado dissipates, and another tornado forms, dissipates, and the debris plumes are really good markers for where these tornadoes are occurring and where they're doing most of their damage, and the debris is going up and then dissipating as the tornado does. So it's a really good tracer of where the damage is happening, and potentially, if you do cross sections to see, the characteristics of the debris plume, lets you know how intense the tornadoes are. So there are 3 tornadoes here. Each one had a slightly shorter path length and was slightly weaker. So we look at the first one, plan view. You had debris way up there, light debris at 18,000 feet. But again, the concentration wasn't that great. So it was taking a lot of leaves and other light material up there, and it was rain wrapped. And that's another reason probably why you don't see a lot of blues there, because there was a lot of precipitation mixing in with the debris. So there's some of the damage it did. This was an EF1, 110 miles an hour, 11-mile path length. Debris plume all the way up to 20,000 feet. So for an EF1, you'd think that's pretty high, but again, a lot of this was light debris, and this was on the ground for 11 miles. So it was able to loft light debris quite a ways up there. And the second one, again, entrained debris up into the updraft. It got all the way up to 15,000 feet. And a lot of this was very little structural damage. In fact, no structural damage that I noticed on the storm survey. Top winds estimate 100 miles an hour, so slightly weaker than the previous one. And path length was pretty comparable to the previous one, but the debris didn't get quite as high. Third one, again, up there near 100 miles an hour. Path length was less, though, about 4 miles, and the debris plume to about 10,000 feet with this one. And again, you'll notice the blues, the higher concentration of debris was low to the ground, and then it probably became less concentrated. And also, again, with a rain-wrapped tornado, probably was lowered by mixing with precipitation. Okay, this is a separate event. This one was notable because it was only on the ground. Damage path was less than a mile, but the debris plume still made it 9,000 feet, and you had some pretty intense damage to light structures and trees, and the debris plume did make it up close to 10,000 feet with this one, and this was kind of a mini supercell and wasn't as rain-wrapped as the previous examples. Here's a fairly weak tornado, EF0, minimal tornado, 80 miles an hour. Path length, about a mile again, debris plume, again, relatively low, and you don't see any blues with this. This was lifting very light debris and mostly leaves. So the debris plume was pretty unimpressive. Another weak tornado with an unimpressive debris plume, only at about 5,500 feet, and mostly leaves and twigs and branches and that kind of thing. So now we'll look at the big dog tornadoes, EF3 and higher. EF3, 150 mile an hour estimated winds with this one in Gaylord, Michigan, May of 2022. Lots of structural damage, lots of debris, and you look in the cross-section and plan view, and you can see up to 25,000 feet. And you'll notice the blue, the 0.8 or lower, is getting way up there to 20,000 feet. That's usually a sign of a big dog tornado, and also that you're not getting a lot of precipitation mixing in with the debris plume. So you look at a cross-section like that, you know you're looking at severe damage, even if the phones aren't ringing off the hook telling you that there's severe damage going on. Another one, this is EF4, 170 miles an hour. Smith Station, Alabama is the top two. The bottom two is Dayton, Ohio, same wind speeds under 70 miles an hour. Path lengths 20 miles an hour or over. Debris plume in the first one, 22,000 feet. And then the Dayton, Ohio one made it up to 26,000 feet. And I think part of the reason why you had a higher debris plume with the Dayton, Ohio one was because you had less of a forward tilted updraft. There was less shear. So I wanted to take a look at how that would affect the height of the debris plume. And there was an extreme case, Winterset, Iowa, March 5th, 2022. Again, EF4, 170 miles an hour, so comparable to the last two. Path length extremely long, 70 miles on the ground damage path. Debris plume was lower, though, 20,000 feet lower than the previous two examples. So I put them side by side, and you could see the forward tilt with increasing shear. So the Dayton, Ohio storm over here on the bottom to the left, 40 knots, 0.6 kilometer shear versus 50 knots for the Alabama storm, and then 70 knots for the Iowa storm. You can see the more forward tilt of the updraft also means forward tilt for the debris plume with increasing shear. And here's a picture of that Iowa tornado, or the parent supercell of the tornado at the time the tornado was occurring, and you could see good indications here of how forward tilted it was. So here's what I did with all the cases that I was able to get a look at and get the storm survey estimated peak winds. I plotted EF scale. You'll notice I'm kind of going by halves here, fractions of the EF scale based on the top winds, and then plotting it against the debris height, the height of the debris signature. And yeah, it's fairly good correlation. There is some variation around the mean, but overall pretty good correlation. So the questions I came up with looking at all these cases were the varying effects of vegetation, storm duration, and wind shear. So I had those three cases of the stronger tornadoes showing that increased shear did result in a lower height to the top of the debris plume. Some other things to look at, various shear cape profiles, path length, foliage or no foliage, meaning is there light debris that could be lofted to greater distances during the summer when the leaves are on the trees versus during the winter when they aren't. So I plotted some of these cases again. I left out the Iowa case because the path length is 70 miles, really skewed this chart. I just capped it at 30 miles an hour, which covered almost all the other cases, and plotted when trees were foliated, which is the F, versus non-foliated cases, which is NF. And you see 3 out of the 4 non-foliated cases were below your expected through the mean, the line of correlation there. So moving towards previous work here, Bodine et al., February 2013, Weather and Forecasting. There's the link to that paper. This was one of the original studies done on looking at debris signatures and their corresponding EF scale tornadoes that were wafting that debris. And one thing to note immediately here is they used 0.82 for your max height, where I was not doing that. I was using what I could see visually as interpolating the height of all the lesser concentration of debris. So you'll notice that when you use the 0.8, even for EF2, you're only getting about 5,000 feet. And some of them, a lot of the EF1s, they don't have 0.8 noted anywhere. So that, again, I saw basically the same thing. A lot of the EF0s, low end EF1s, you didn't see, especially when they're further from the radar, you didn't even see 0.8 or lower. But once you get up into the higher ranges, the EF4s, EF5s, you'll see that 0.8 get way up there, over 20,000 feet. So quick rule of thumb, if you're seeing blue in your cross section, 15, 20,000 feet, you're looking at pretty significant damage, possibly a violent tornado. Some other factors go into that, obviously, like forward tilt to the updraft, and also mixing with precipitation, which would occur, in your more rain-wrapped tornadoes. So another thing that I discovered during this project, which has implications for our tornado climatology, are some very weak circulations that do produce weak debris signatures. And, we surveyed a couple of these events and couldn't find anything except a few, leaves. There were no trees on that we could find. So we're wondering, if these things are more common than we think and that, we could be looking at a lot of them. Here's one example. You had 25 knots rotational shear, and you had, debris signature up there. And this is, again, fairly close to radar at 1,000 feet, and sometimes up to 5,000 feet. Here is a line of them at this loop. You got reflectivity, and it's basically a good convergent shear zone here where you get little misocyclones, and you can see a whole string of debris signatures here. And, the question becomes, do we want to call these tornadoes? And if we look at one example of this, again, very weak rotational shear under 30 knots, but it is lofting light debris. You don't see, a lot of it, but there is some, even some 0.8 or lower right near the surface there. So the question becomes, do we want to call these tornadoes if we can't find debris? The EF scale, EF0 has a lower bound of 65 miles an hour, and if we can't confirm winds at that speed, what do we call it? Obviously, there's not an EF -1, so it doesn't meet the EF0 criteria of 65 based on a storm survey. What do we do with that? So quick summary of the findings. Max height correlated to tornado intensity duration. Debris height increases with EF rating and path length duration. We found that the vertical wind shear and ability of light debris could be an issue with how tall the debris signature gets. And then again, those small, shallow misocyclones and their debris can be detected by radar, but I'm not sure we really want to call those tornadoes. So at this point, I'll open it up to questions.
All right. Thanks, Ernie. Otherwise, thanks for your time and attendance today, and hopefully you enjoy the rest of your day. Thanks a lot, everybody.